Okay, students, on this online classes on electrical machine second, we will be studying today lecture 1, that is equivalent circuit of three-phase induction motor. We will be making the final equivalent circuit of induction motor in this first lecture. Okay, now let's begin with before making our equivalent circuit, we need to know some basic quantities. We have discussed this in previous classes. You must know what is slip. The slip is it is the difference between synchronous speed and the actual rotor speed. Uh, so the formula of this is ns minus nr upon ns into 100, where ns is RMF of stator or synchronous speed, nr is the actual speed of rotor. This both 2 points A and B we have discussed earlier. That uh, at starting the induction motor doesn't have any speed, so the rotor speed should be 0. And by this formula, ns minus 0 upon ns, the slip must be 1 at running condition. So let's assume that our motor is running at synchronous speed. Suppose, okay, at this ns minus nr is equal to ns, so the slip becomes 0. So when induction motor attains its speeds from 0 to ns, the slip attains its value from 1 to 0. Operating slip range generally varies from 1 to 3%, but the slip, or you can say the operating region of slip, is very less, and you can see it is only 0.01 to 0.03 unit. Okay, so the operating region of slip is very less. If the slip increases, automatically efficiency decreases. This we will see in our top derivation. Now, in a second, we can see the effect of slip. Okay, what is the effect of slip? Due to slip, the rotor, what are the effects the rotor is facing? So this is the circuit. The first one circuit is in star connection, that is stator side, which is stationary, and the second circuit is our rotor circuit. Okay, which is movable. Okay, the rotor is a rotating part, where stator is stationary part. We are dealing with our per phase values. So at starting, as we discussed earlier in previous slide, that at starting nr is 0, the slip is 1. So we are deriving this expression of slip when the rotor is stationary or at starting. Okay. Now when we apply a three phase voltage V1 at stator side, a rotating magnetic field produced in the air gap, and due to this rotating magnetic field interacts with the rotor side, and an EMF is produced in the form of E2, and the current I2 flows, and this current is flowing in rotor conductors, and the rotor conductors are also facing a RMF. Then this conductor will experience a force, that is a Lorentz force, and will try to rotate, and this is how rotor starts moving. So these are the quantities, and I have made the secondary terminals of it as short circuit, V is equal to 0. Now from secondary side, you can see that I2, that is the secondary current, it will be E2. E2 is my per phase quantity upon total impedance of per phase, that is R2 and X2, so under root of R2 square plus X2 ka whole square. This can also be written as E2 minus I2 R2 plus JX2 is equal to 0. Okay. Now at standstill, the frequency at standstill when the rotor is not moving, as you can see that P, this formula we have uh, studied earlier, that F is equal to NP upon 120. So this is difference, NS minus NR. So ns is the synchronous speed when standstill, and nr is not moving, so its speed should be 0. So this, the frequency at standstill is equal to p ns upon 120. Now at running condition, uh, now the rotor has some speed, it is denoted by nr, So the f dash will be ns minus nr. So from these two equations, we can see that f dash upon f is equal to slip. So the f dash is the running frequency or the rotor frequency is slip times of the original frequency. Suppose the slip is 1% and frequency, as we usually know that it is supply frequency 50 hertz. 50 into 1% will be 0.05. The slip frequency 1%. 1 upon 100 into 50 will be zero point 0.5. So the rotor frequency is only 0.5. You are supplying a 50 hertz and you are getting at rotor side is zero point 0.5 hertz. So due to slip, the frequency reduces on the rotor side. So the first was effect of slip on frequency. Okay. Now second, effect on voltage. So what will be the effect of voltage? If suppose here E2 is our voltage when the rotor is not moving, that is standstill. E2 dash is our voltage when the rotor is moving. So what is E2? E2 is our secondary or rotor side induced voltage. So we have seen that E2 is directly proportional to the change in speed of slip. Ns minus at start s is equal to 1. So E2 is proportional to 1 only. E2 dash is proportional to ns minus nr at rated speed. So from this we can see that E2 dash is equal to S of E2. Again the supply, again the secondary voltage of rotor side or the rotor when moving has become S times of E2. Again the voltage has reduced due to slip. Now last is the effect of rotor resistance. Sorry, not last, third, effect on rotor resistance. Now R2 dash and X2 dash. Now the rotor, there will be no effect on R2 dash as resistance does not depend on any other external parameters. Now what is X2 dash now? X2 dash is reactance that depends on slowly on frequency. So the frequency will reduce, the reactance will also reduce. So X2 dash will also become S of X2. And the final effect of power factor. As you know, in a circuit, power factor is R upon Z, as we can draw it from a power triangle. So cos phi is equal to R upon Z, R under root of R square plus X2 square. But still R does not depend on slip, but X2 depends on slip directly. So instead of X2, there it must be S of X2 when cos phi is my power factor at stationary, when the rotor is stationary, and cos phi dash is a power factor when the rotor rotates. Okay, so again I2 dash will be S of E2 upon under root of R2 ka square plus S of X2 ka whole square. So this is the current in the rotor under running condition at slip S. So instead of E2 we have got S of E2, and instead of X2 we have got S of X2. So I think that's enough for this lecture. We will be continuing this lecture in part second.